Well, welcome to the videos for Shaughnessy's class, Math 30-2. Once again, the basic disclaimer. Please make sure you're showing up to class. This is Probability and Set Theory, Lesson 7. It's talking about mutually exclusive versus non-mutually exclusive probability and situations. So please, if you have any questions, just let me know. Continuing on with this. Now, this lesson starts with a whole bunch of notes. Okay, if you're just watching this now for the first time because you missed class, I'd recommend you pause it right now and copy down some of these notes. Now, going along with this, when we consider possible solutions, okay, single events are occurring. Okay, sometimes it's a single event. Now, that single event can satisfy a bunch of different things at the same time, or sometimes multiple events can happen at the same time. So in this case, if you consider a deck of 52 cards. Now, a deck of 52 cards has 4 suits, 13 different cards within each suit. There is one of each suit for each of the aces, 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, as well as Jack, Queen, King. If you consider this situation, this is a first example. If you consider this situation and the context wants us to draw one card from this deck, and the probability of drawing a red card or a diamond, okay? Let's pretend that's what's going on. A red card or a diamond. The thing about this that's weird is the fact that diamonds are red. And so when you go through this, you've got situations, you've got cards that are both. You've got cards that are diamonds. And if you get a diamond, you've also got a red card along with this. This is non-mutually exclusive because they can occur together. The easiest is to look at mutually exclusive and realize that non-mutually exclusive is the opposite. So in this case here, in the second example, one card, and I need a red card or a spade. There are no cards in that whole deck that are going to be spades that are red, unless it's some sort of trick deck. If it's a standard deck, there are no red spades. Because there are no red spades, you get this idea that, you know what, it doesn't really overlap. It doesn't end up satisfying both at the same time. This is mutually exclusive. Together, they don't overlap. They are standing out on their own. There's a red card, there's a spade card, and even though they're part of the same context, same question, same situation, they don't overlap. One excludes the other and vice versa. So the two terms that come with this are mutually exclusive, non-mutually exclusive. Now, I'd like to use something different, but the term that we use is non-mutually exclusive. So basically, that's what it boils down to. It's either mutually exclusive or it's not. Okay? That first one where you've got the red and the diamonds way up here, the red and the diamond, that's non-mutually exclusive. There is the possibility of having both happen. So they don't stand apart, so they don't stand separate, so they're not mutually exclusive. So you get these two terms. Mutually exclusive events are events when there is no probability of multiple events occurring within a single element. You can't make both happy. That's the red card and the spade. You can't get a red card that is also a spade. It's just not possible. Non-mutually exclusive events are events where it is possible to have both of them happy at the same time. It is possible to have the multiple events occurring within one single element. I look at one thing and it's both. Okay? So if I look at these examples down beneath here, okay, and I'm just going to move this up. All of these terms go along with this. An experiment involves randomly selecting, okay, a single token from a group of 8 different colored tokens. The red token and the blue token also have a white dot placed in their center. That's placed. Okay. Okay. So the red token and the blue token, they all both still have a white dot. Okay. Classifying the following events as mutually exclusive or not mutually exclusive. So if I say event A, or the probability of A, is selecting a yellow token. Okay, so event A is selecting a yellow token. Okay, if I look at event B as selecting a green token. Okay, In these particular cases, they're mutually exclusive if they both can't happen with the same token. They are non-mutually exclusive if they can. So look at these. There's a yellow token, there's a green token. There's no token that's going to be both. Since there is no token that's going to be both, they are mutually exclusive. I'm just going to write ME for now. Okay? Mutually exclusive. Okay? They are mutually exclusive. There is no way you can select a single token that's going to make both happy. Okay? If I define event A, in question B, if I define event A as selecting a yellow, and event, I'm going to say C because it's a different one, of selecting a white dot, okay, is there any token that's going to be both yellow with a white dot? So I go back and look at this. Okay? An experiment involves randomly selecting a single token, 8 different colors. The red and the blue each have a white dot. In this case here, I'm not talking about the red and the blue. Only the red and the blue have the white dot. There's no way I can get something that's yellow with a white dot. So once again, these are mutually exclusive. Okay? If I look at C, probability of event, and I'm just going to call it D, is selecting a red. And the probability of event C, again, is selecting a white dot. Okay, so D is event selecting a red. Once again, C is selecting a white dot. And I ask myself, is there anything that would satisfy both at the same time? And for this question, yes. The red and the blue token each have a white dot. So if I get the red token, I've also got the white dot. If I get the white dot, I also could have a red token. I may not, but I could. There is the possibility that they go together. So this is non-mutually exclusive. Okay. Non-mutually exclusive, because there is the possibility they occur together. Okay. It doesn't have to do anything with the red, though. Probability of selecting a red. And if I say the probability of event E is selecting a blue, okay, they both share the white dot, but neither one of the events is concerned with the white dot. I can't select a token that is both red and blue at the same time. Okay? It's not talking about the white dots. The events themselves are not defined in terms of the white dots. So because of that, it's mutually exclusive again. So it's not just selecting these ones. It has to do with the events themselves. Do the events, or is it possible for both of them to be satisfied at the same time? Okay? Now, keeping in mind ME is mutually exclusive, I'm going to write that here. Mutually exclusive, and NME is non-mutually exclusive. Please don't forget that that's what I'm saying, okay? I was just limited on my room, so I wrote the letters here, okay? I'm defining what they are, okay? But nonetheless, that's mutually exclusive or non-mutually exclusive. Once you're comfortable with that idea, okay, there's terms that go along with this. If I look at this one, in a group, sorry, I'll focus this again. In a group of 50 students, there are 40 students taking English and 20 students taking bio. An experiment involves randomly selecting a student from this group. Event A is selecting a student taking English, and Event B is selecting a student taking biology. Are A and B mutually exclusive or non-mutually exclusive? Okay, so I look at this. There's 50 students in total. Okay, 40 of them are taking English, 20 of them are taking bio. Now, if I look at that, that's 60 students. Okay, I can't have 60 students. So what that's telling me is if I have 60 students mentioned over here, but I really only mentioned 50, I only interviewed 50, then from these 60, there has to be some form of overlap. If this was 10 and this was 20, I wouldn't know for sure. I wouldn't be able to tell. But because that's 50 and I've got 60 students over here, there have to be some that have been counted twice. And when they're counted twice, it means they're in the English group and in the bio group. And so if they're in the English and the bio, they're linked together. And so if they're linked together, they're non-mutually exclusive. Because mutually exclusive would be separate. Non-mutually exclusive means you can have both. So the question here is, are these events mutually exclusive or non-mutually exclusive? I would write the following. These are non-mutually exclusive. Now that's not everything I need to write, but these are non-mutually exclusive. This is because in the description, for English and social, English and bio, there are 60 students mentioned. As we only considered students, we know some students are counted twice. This means they are taking both English and bio. And because there's the possibility of selecting these students, that's why it's non-mutually exclusive. Okay? So it comes purely from the context and what's the situation, what are we looking at. Now when it comes to calculating these probabilities, you have to consider that in some cases there's an overlap, or there's students that are counted twice, and in some cases there's not an overlap. If they're mutually exclusive, okay? If they're mutually exclusive, it means there's no chance that they overlap. There's no students that are counted twice. So if they're mutually exclusive, okay, what I end up with is the probability of A or B. There are no overlaps, there are no students counted twice. So it's going to be the probability of A plus the probability of B. Okay? Or could mean union as well. So the probability of A union B is the same thing. This is if they're mutually exclusive. If they're non-mutually exclusive, then that means you've got kids counted twice. You've got situations counted twice. So if it's a non-mutually exclusive situation, the probability of A or B is going to be the probability of A plus the probability of B, but you've got to subtract one version of the overlap, minus the probability of A and B, minus the ones that are counted in A and counted in B, because I've counted them both here. I counted them here, counted them here. So I counted them twice, so I have to subtract one counting. Okay? In that case there, you've got the same thing. So you've got A or B, okay, A or B, and that's the probability of A plus the probability of B minus the probability of the intersection of those. So A or intersection B. Okay, you've got that overlap. And so when you've got these sorts of things, you kind of just go. Sorry, I paused it for a second. I'll have to refocus. So once you've got these formulas you're comfortable, you realize that mutually exclusive, non-mutually exclusive are essentially the same thing with the connections. So if I look at this one, an experiment involves selecting a token from a group of 7 red tokens, 5 blue and 2 yellow. So looking at that, 7 plus 5 plus 2, there's 14 tokens in this bag, okay, or in this situation, group. a white dot is shown on 2 of the red tokens and 2 of the blue tokens. What is the probability of selecting a red token? Well, probability is favorable over possible. So the probability of a red token is favorable over possible. There are 7 red tokens out of 14 tokens. So it's a 1/2 probability. That's simple. That's an easy question. Okay. If I look in B, B here is a red token or a token with a white dot. So the probability of a red or union, a white dot, a white dot, is going to be the probability of a red token, okay, which I just did, plus the probability of drawing a white dot token, minus the probability of having red and white dots. Okay? I've got to count those ones because some of those white dots are going to be red. So this is a non-mutually exclusive situation. The probability of drawing a red token I actually did up here. It's 1/2, so I'm just copying it. The probability of drawing a white dot. Well, I go back up to the situation. There are 4 white dots. So 4 out of my 14 are white dots. So I'd add those together. But some of those white dots are also red, so I've got some overlap going on here. In fact, 2 of them are red with white dots. So I've got to subtract the 2 out of 14 from that one. So I have 1/2 plus 4 out of 14 minus 2 out of 14. And I go on my calculator and figure that out. Okay. Use fractions, all that sort of thing. And I'm just typing it in right now, so sorry it's taking me a moment. And I'm going to get that this is 9/14. Okay. So there's a 9 in 14 chance that I'm going to get a red dot, or sorry, a red token, or a white dotted token. Okay. But I have to remember that since there's overlap, this is non-mutually exclusive, so I have to remember to subtract those things. Okay. So once you're comfortable with this idea, that's all that goes on. I'm taking the same context, so I hope you're okay with this. A blue token with a white dot. Sorry, blue token or a token with a white dot. So keeping in mind, this is the probability. This could be non-mutually exclusive, so a blue or a white dot. Okay. It's non-mutually exclusive, so I know it's going to be the probability of drawing a blue token plus the probability of drawing a white dotted token, minus the probability of drawing the blue and the white dot. Okay? So going from there, blue tokens. I'm looking in here, there are 5 blue tokens out of the 14, so it's 5 out of 14. Plus, white dots. Well, there are 4 with white dots, so it's plus 4 out of 14. However, since I can have a blue token with a white dot on it, okay, then I've got to subtract those blue tokens with white dots. There are 2 of those. So minus 2 out of 14. So 5 plus 4 is 9, minus 2 is 7. So I'll get 7 out of 14, which does reduce to 1/2. But nonetheless, that's going on there. Now, you don't always have to do the subtraction. Okay, you're going to see that here. The probability of drawing a red token, or, not 4, or a yellow token. So that's the probability of drawing a red token, or a yellow token, okay? And that's going to be the probability of the red plus the probability of the yellow. And that's it. The reason being is these are mutually exclusive situations. You don't have any tokens that are red and yellow at the same time. It just doesn't make any sense. So because of that, I don't have to think about the subtraction. The probability of getting the red tokens is 7 out of 14. We did that a few minutes ago. Plus the probability of getting a yellow token. Okay, I have to go back and look. There are 2 yellow tokens, so it's 2 out of 14. Add those together, I'm going to get 9/14. Doesn't reduce. There you go. It's still a situation where I'm adding. It's still a situation where I'm doing this or this. But you have to look at the situation to determine whether or not you have to do the subtraction. Okay? Now you can say, well, you know what, Shaughnessy, we've done this with B and C, and they were both a colored token with a white dot. So as soon as I throw in the white dot, I have to subtract. Well, that's not true. If I do E, a yellow token with a white dot, that's the probability of a yellow token or a white dot. There are no tokens, and I look back at the context, but there are no tokens that are yellow with a white dot. So I don't need to subtract. It's the probability of the yellow plus the probability of the white dot. There is no need to subtract here because these are mutually exclusive events. So there are 2 yellow tokens out of 14. There are 4 white dots out of 14. So it's become 6 out of 14, which reduces to 3/7. Okay? And so on and so forth. So you've got that. So this is just sort of the idea. Now, once you're getting comfortable with the probability, then I can suddenly throw odds back at you. F. What are the odds in favor of drawing a red token or a token with a white dot? Odds. It's not probability, I know that. I have to figure out the probability of drawing a red token or a token with a white dot. Now, I did that. That's question B. Okay? So I'm going to just from B, I'm just going to put it here. From B, I know it's 9/14. If you didn't have it, you'd have to do it. But I know the probability of getting a red or a white dot is 9/14. So when I look at this and I need odds in favor of doing this, well, there are 9 favorable outcomes out of the 14. How many of them are unfavorable? How many of them are not a red token with a white dot? 14 minus 9 is 5. The odds are 9 to 5. Sounds like a movie, but the odds are 9 to 5 that you are going to get a red token or a token with a white dot. Okay, so you need the probability, but then you can work backwards. 9 to 5, odds. You have to look to see what the question's asking. Okay, we are going to try to trick you. We're going to give you probabilities when we want odds to see if you're paying attention. We're going to give you odds when we want probability to see if you're paying attention. You're reading that word. My recommendation, go through and circle it. Odds, you see odds, circle it. Okay, in all of these, A, B, C, D, they were all probabilities. So we're just going with that. So once you've got the idea of the probability or the odds, you've got to make sure that you can figure these things out. So, I look at this next example. If A and B are mutually exclusive, the probability of A is 0.3, the probability of B is 0.17. Find the probability of A union B, or A or B. Okay, they're mutually exclusive. Since they're mutually exclusive, I don't need to consider overlap. So in this case, the probability of A or B would be just the probability of A plus the probability of B. That's all I would do. And in this case, the probability of A is 0.3. The probability of B is 0.17, 0.47. And I'd round to whatever the question wanted, but that's what I get. Okay, mutually exclusive, it's that simple, just add. I could give you one side and make you use algebra to find the total and make you use algebra to solve for it. Either way, that's all same and good. Okay. The key thing is sometimes we give you other stuff. If I do this one here, okay, now there's not a lot of space here. If A and B are non-mutually exclusive events, P at A is 0.3, P at B is 0.17, P A and B is 0.03. Find A or B. Well, since they're non-mutually exclusive, okay, and I'm putting it up above because I didn't put enough space here. Or maybe I'll put it in here. P of A or B equals the probability of A plus the probability of B minus the probability of A and B. Okay, so that's the formula. The probability of A is 0.3. The probability of B is 0.17. The probability of the both of them is 0.03. And I worked that out. Now that's going to be 0.44. Okay, so the probability of A or B occurring is 0.44. Okay. If I do this next one, if A and B are non-mutually exclusive, P at A is this, P at B is this, and P A or B is 0.5. You've got to keep in mind, well, if it's non-mutually exclusive, you know P of A or B, and this is given on the formula sheet, is equal to P at A plus P at B minus the overlap. Okay? Now this question here is wanting the overlap. You can see that because it's exactly the same. Okay, you know that from the symbology, you know what the symbols mean. You know that's the P of intersection A and B. all that sort of jazz, so I need that. So this is one where I'm talking about, you have to work backwards. P of A or B is 0.5. So 0.5 equals P at A is 0.3, P at B is 0.17, and P A or B, A and B, is unknown. So using algebra, I get 0.5 equals 0.47 minus P of A or B. Now this isn't going to make any sense, okay? So I've got to go back and figure out some things. So going through with this idea, I'm going to change this question just because I notice this isn't making any sense. So that's got to be 0.4, which means that's 0.4, and that's 0.4. Now when I subtract, I'm going to get 0.07 equals negative P, A, and B. Divide by the negative, I'm going to get the probability of A and B occurring is 0.07. Okay? So I get that done. So sorry about that change. This was 0.4, so which means I changed those and those to 0.4. Okay? It was just because the math didn't work. It's kind of something that happens. Okay? Going along with this then, B, what are the odds in favor of this occurring? What are the odds in favor of this? Okay? Now, that there is 0.07. As a fraction, that would be 7 out of 100. So I'm looking for the odds in favor. The odds in favor, there are 7 favorable events. Okay? 7 out of 100 is the probability. If there are 7 good events, there are 93 bad events. So 7 to 93 are the odds in favor of this occurring. And so that's what you end up getting. You kind of work with that. Okay? Keeping in mind, along with this, there is going to be some homework. So please make sure that you do the homework. Please make sure you come to class. And otherwise, have a marvelous day.